Hey, everybody.
How you doing, Dr. Chan?
Good. How are you?
Not too bad.
Good, good.
How's it going, Dr. Tran?
Good, good. How are you?
Doing all right. Just got out of propulsions with Dr. Wang.
Oh, how's that going?
It's cool. We just learned about thrust.
Nice, nice. That's good. Yeah, propulsion was something I was always interested in. I actually wanted to study it in grad school, but I ended up doing something else.
Well, so far it's pretty neat. I like it.
Nice, nice. That's good.
I haven't cried yet, so that's a plus.
No crying at the end of first week. That's always a
Yeah.
good thing.
Hey, Professor, how's first week of going for you?
Rest of my first week?
Yeah, how's the first week going?
Oh, that's good. Stuck at home. You kind of feels like we went back a year because this is what we were doing, last year. But I like it though because I actually teach one more class after this, and so I go until 8:30 every day. So I would rather be in my home at 8:30 rather than on campus and having to drive back after that. So
Makes
I'm
sense.
actually not looking forward to when we go back. Actually, let me get some water. Oh, question in the chat. Oh.
How's your cardiovascular class going?
It's good. Yeah, we just had one class so far. So we just kind of introduced the class. I think a lot of people are pretty excited for it. So we'll see.
Yeah, that's cool. Yeah, I signed up for it, but I kind of want to take heat transfer. I feel like, well, I like both, but like I can only pick one due to my schedule.
Right. Understandable. Yeah, both classes are great. Hey, Samson. That's good. Yeah, it's Mondays and Wednesdays are my long days. So I have one more class after this. And so normally I start my day in the morning just because I'm a morning person, but I think this semester I'm gonna have to adjust because I go so late. So I actually went to Costco this morning to do my shopping. That's how I started my day. It's nice. There's only old people there at Costco in the morning, so I didn't have to fight anybody. So that's always a good thing. All right, it's 5:30, so let's go ahead and get started today. Good evening, everyone. How's everyone doing today?
Doing good.
Good, good. Thumbs up, thumbs up. Yeah, it's the first week. Everyone's still happy. No stress yet. So that's always a good thing. But I know things can ramp up pretty quickly. Okay, and so so this is our second class session, and so Monday we kind of just introduced the class, just kind of talk about what the class is about. Today we're actually going to start learning stuff. Okay, but to that end, I thought one thing I would do is just do a little bit of review today. And so because this class is called computational heat transfer, I thought I'd review just kind of the main concepts of what we're going to need from heat transfer and fluid mechanics. And what you'll see is it's actually very little. And so the only thing I'm going to really remind you of is just what the equation looks like, because we're really just going to be working directly with that equation. And so a lot of heat transfer you're not actually going to need in this class. Is just you just need to remember what the equation looks like, and then we'll talk about how we're going to proceed for the next few weeks. Okay. All right. And so right. And so that's and so I think that's all the info I have for right now. Are there any questions I can answer before we get started? Okay. All right. So let's go ahead and get to it. All right. And so today, even though last time I did kind of an overview of the course, kind of the title that I have for these notes is called Introduction to Computational Heat Transfer. All right. And so the reason, the reason I call these notes this is, probably for a lot of you, this is the first computational class that you've taken. Maybe you've taken finite elements, and that's kind of in the same vein. But I thought I'd kind of reintroduce a lot of that stuff from scratch, just because I think it's kind of a good starting point. Okay. And so the whole idea with doing computational heat transfer and for doing just engineering analysis in general is that a big part of it is, we want to determine, or we want to predict what will happen to our physical systems of interest when we apply external effects. Okay, so basically, a lot of engineering, we have these physical systems. We have our systems of interest, and they're going to be exposed to external effects, whether it be external forcing, or in this case, external heating, temperature distributions, and things like that. We want to be able to predict what's going to happen to this physical system before we actually do it. Okay. Okay. Because most engineering systems kind of fit under this category, right? And so if we can predict what's going to happen to our system when it's exposed to these external effects, we can design around that, or we can design a better system, or we can optimize it under under new conditions. Okay. And for the systems that we're going to look at in this class, which are mostly thermal systems, these are typically very challenging to analyze, just because the heat equation and for the fluids case and the Navier-Stokes equations are usually very difficult to analyze. Okay. All right. And so to that end, some example systems like that we can analyze with the or I should say, excuse me, Some example fields that we can analyze using the techniques from this class would be areas like HVAC, heating, ventilation, and air conditioning. Okay. Okay. That's a very popular application of the topics in this class. Okay. Another popular application is pipe flow. Right. So obviously that's a lot more on the fluid side. Okay. There's electronics, right? And so electronics is a, the thermal design of electronics is something that's really important. Okay. And lastly, we have aerospace. And so aerospace has a lot of very complex systems that are, designed on kind of very razor thin margins. Okay. And so, to perform engineering analysis, to perform these predictions, there are multiple ways that we can go about it. Okay. And so I have three different approaches to what I call engineering analysis. Okay. Okay. All right, so the first approach that we have is what I like to call an analytical approach. And so this is the approach you're probably most familiar with from your previous classes. And so what this approach involves is using pencil and paper to solve the fundamental governing equations. Okay. Okay. And so the first time you've taken heat transfer, the first time you've taken fluid mechanics, or first time you've taken strength of materials, right? Most of those classes involve, looking at a problem and solving them by hand using all the governing equations, right? So all of those kind of fit into this category of analytical problem solving. And so the benefits of analytical problem solving is that it's normally very fast, right? You may not think so, but actually solving a problem by hand, even if it takes you like an hour, that's actually pretty fast compared to what it could be, right? And it's very inexpensive because all it takes is basically just a piece of paper and a disgruntled engineering student, right? Which is normally very, very cheap, right? So it's fast and cheap, which is good. But usually when things are fast and cheap, it comes with the caveat. And the caveat being that it's very limited to just simple situations, right? And so think back to the problems that you've solved before in your previous classes. None of them were ever too complex, right? And it's not like you can go and design an entire rocket with just hand calculations, right? That would be really hard to do because a rocket ship is very, very complex. And so even though analytical solutions, they have their place, and so I'm not saying that people don't use them, but they aren't often used for practical problems because of the limitations of the complexity that you can handle. Okay. Sorry. Okay. And so they can only be used for basically the simplest of the simple problems. Okay. But they have their place. Okay. And I think I think as a student, I always found it comforting to know that professional engineers, they don't really get that much better at solving hand calculation problems. You know, kind of actually right now, you guys are kind of peaking at your problem solving capabilities. So, you know, it's not like professional engineers are sitting down with pencils and papers and solving, you know, galactic brain, you know, rocket ship problems, right? And so, you know, actually, I would say most people kind of forget how to do those in their professional career. But a lot of the intuition and a lot of the conceptual knowledge really sticks. And so, you know, analytical problem solving, it has its place, but you know, it also has its strong limitations as well. Okay. So that's approach number one. Okay. Any questions on this so far? Okay. All right, so that's the first approach to engineering analysis. The second approach is kind of almost the exact opposite of analytical, which is an experimental approach. Okay. And so an experimental approach is to basically just design an experiment or design a physical test to you know, to see what's going to happen. Okay. And so this is great. And this is something you probably all have experience with as well, because you know, you got this through your lab classes. And the nice thing about experimental techniques is that it gives you usually the best, most reliable data. Okay. There's no one that's going to dispute the results of your experiment because, you know, it actually happened, right? And so that's as opposed to analytical solutions where, you know, a lot of times you have to make assumptions and you can make mistakes in your mathematics, you know, and then there's a lot that can go wrong in an analytical solution. But for an experimental situation, you know, it actually happened. And so there's really no disputing that at all. Okay. The downside to setting up experiments is that relative to analytical and technique number 3, which we're going to go over soon, it's very expensive and very time consuming. Right. If you wanted to test something on an airplane, you know, it's very expensive to build an entire airplane to test your hypothesis, right? And so, you know, we kind of have these two extremes. And so we have analytical solutions, which are, you know, very cheap and fast, but only work for simple stuff. We have experimentals where, you know, you can handle basically any level of complexity that you can imagine, but it's extremely expensive and very time consuming, right? It'd be nice if there would be something kind of in the middle of that kind of gives you a little bit of the best of both worlds. And that's going to be technique number 3, which is computational. Okay. And so computational, you know, it's actually, you know, closer to analytical in the sense that, you know, we're making predictions based on the governing equations. Okay. Okay, but instead of solving this by hand and using a human brain to solve these, we're instead gonna use computers. Okay. Okay. And that has a lot of benefits because remember what we talked about last time. computers can do calculations that, far exceed, human capabilities. They're way faster than computers, or if they're way faster than humans. And because they have that speed, we can throw at it, much more complicated situations. And so computational approaches are great because they can handle, complex cases, but it can do them without wasting a bunch of time and energy. Okay. Okay. And so we kind of get a best of both worlds here, where we can handle the all the complexity that comes with a practical situation, but without the time and without the expense. Okay. The tricky thing with using computational methods, and you'll learn this very quickly in this class, is that they can be very, very tricky to set up. Okay. They can be tricky to set up, and they can very easily give you deceiving results as well, right? I can't tell you how many times that in the past where I've seen people, use some kind of computational code, or they've written their own computational code, and they get a result that they think looks right, because the computer kind of makes everything kind of seem nice, but it's actually completely wrong. Okay. And so even though computational, it's a very valuable tool, and people are using it more and more, you have to be kind of careful in setting this up. And that's what we're going to learn in this class is how to set up these kinds of problems, how to write the code to actually solve these. Okay. One thing I always like to tell people is that computers are extremely powerful, but they are the dumbest powerful thing that you will ever see in the world. Okay. Okay. Computers will do literally anything that you tell it to, but you have to tell it to them in like a very precise, very kind of very kind of step-by-step process that I think a lot of people just aren't used to thinking about. And so when you're doing programming, think of your programming as you're giving your computer instructions on how to do a calculation. You have to be extremely precise, and you have to be extremely detail oriented and very nitpicky about how it does every single little thing. Because a lot of things that I think as humans we kind of assume and we kind of take for granted, the computer it has to be told exactly kind of what to do in those situations. And I think that's the thing that I think people kind of struggle with programming is doing that. So think of your computer as like a baby, but an extremely powerful, extremely fast computing baby. And so the same way that you try to teach a baby to do a simple task, like maybe like brush their teeth or something like that, right? Think of doing your computer as kind of the same way. And we'll go through this throughout this class, quite a bit. And everyone, I think everyone in this class will be frustrated with MATLAB at some point because you wanted to do one thing, but MATLAB does another thing because that's what it thought. So just kind of keep that in mind, that your computer in MATLAB is like a really powerful baby, and you just have to kind of treat it as such. All right, any questions on this so far? Okay. All right, and so now that we have that intro part out of the way, let's go ahead and launch into our review of heat transfer and fluids. Okay, it's going to be extremely brief. You'll see that you'll need very little of it, but but I do want to at least review the equations. All right. And so I'm grouping these two together. I know that there's separate classes in our department, and they should be, okay, but they actually share a lot of similarities with each other in terms of their equations, okay. And in particular, we're going to look at the two, I'd say, primary equations within these two subjects, right? And so for heat transfer, the primary equation for that is the heat equation. Okay? And so you hopefully you'll remember the heat equation from heat transfer, okay? Or at least remember about the existence of the heat equation. That's all I need you to remember, okay? And the main equation that we used in fluid mechanics was the Navier-Stokes equation. Two very complicated equations, from two classes. But what I'm going to show you is that maybe you've kind of noticed this before about these equations, but they're actually very, very similar to each other. And they, and once you see them kind of side to side, you'll see that maybe they're almost exactly the same. Conceptually, they kind of represent the same thing for each of those two subjects, in that they're both what I like to call a conservation equation. Okay. In that they represent the conservation of some kind of quantity. Okay, so for the heat equation, that it represents the conservation of energy, whereas the Navier-Stokes equation represents conservation of mass and momentum. All right, so let's go ahead and write out the forms of these equations. And in fact, I'm going to write out the 2D forms of them. Okay, and so let's start with the heat equation. Okay, so this is 2D, right? And so the heat equation is given by the following formula. And so we have rho times Cp, and I'll define all the terms in a bit. Times partial T, okay? And so that's the derivative of the temperature, which is capital T, by time, which is little t, okay? Plus U, partial T, partial X, okay? V, partial T, partial Y, okay? Where U and V here are velocities, okay? This is equal to K times partial squared T, partial X squared, okay, plus partial squared T, partial Y squared, okay, plus Q dot, okay, where Q dot there is our production term. All right. So there's our heat equation. Maybe the heat equation that you saw in 407 might look a little bit different, but this one takes into account unsteadiness, and it also takes into account convection as well, okay? So let me go ahead and define all the terms that we have here, okay? So big T here, this is temperature. Okay, rho is density. CP here stands for specific heat. Okay. K here is thermal conductivity. Okay. And Q here is a thermal production term. All right. And so that's our heat equation, and this includes both conduction and convection. Okay. All right. Any questions on this so far? Question in the chat. Heat rate. Yeah, so Q dot can also be like a heat, a rate of thermal production. Yeah, heat or a rate of heat production. Yeah. Okay. All right, so that's the heat equation. I'm going to break it down in a second, but I think first I want to show you the Navier-Stokes equations. Okay. Or I'm just going to show you one Navier-Stokes equation because there's actually four of them, but we only need one of them now for our purposes. Okay. All right, so let's look at the Navier-Stokes. Okay. And again, this is Navier-Stokes in 2D. Okay. All right, and so we have the density rho multiplied by partial u partial t. Okay, where u here is actually a velocity. Okay. Okay. Then we have u times partial u partial x plus v times partial u partial y. Okay, this is equal to minus partial p partial x, where this is our pressure term. Okay, plus mu, where mu here is the viscosity. Right, and this multiplied by partial squared u partial x squared plus partial squared u partial y squared. Okay, plus rho g. Okay, where that last term is our gravity term. Okay. Right, and so there is our Navier-Stokes equation. Okay. All right, so let's go ahead and define the terms here. Okay. And so the terms that have the same symbols as the heat equation, I'm just going to leave those the same. Okay. And so u here is our x velocity. Okay. V here is our y velocity. Right. P with the ponytail, this is our pressure. Right. Mu here is viscosity. And G is our acceleration due to gravity. All right. So those are our two main equations that that we had when we were solving for heat and for fluid mechanics phenomena. All right. And so why am I giving you these two formulas again? Right. So remember I mentioned before that these two formulas have a lot of similarities with each other, right? If you haven't started to see them already. And so even though the quantities that we're solving for are different, the equations themselves have very, very similar structure. Okay. And I'm gonna show that to you right now. And so I'm gonna break up, I'm gonna break up these equations and we're gonna go kind of term by term, and I'll show you that each of them actually represents kind of the same thing. Okay. All right. And so let's start with the time derivative term. And so the time derivative term in Navier-Stokes is partial u partial t. And in the heat equation, it's partial t. Okay. And so I'm circling both of those in red because they represent the same thing. Okay. And so our terms in red here represent what I call unsteadiness. Okay. And so what this term basically represents is the fact that our quantity of interest, or in this case, our conserved quantity, can change with time. Okay. Right, and we can observe this too, right? And so if you look at any fluid flow situation, we know that the fluid flow phenomenon can change with time. Okay. And so one other important note about the unsteady term is that we set it equal to 0 when we make the steady state assumption. All right. And so that's the unsteady term. Okay. All right. So the next group of terms that I'm going to look at are these two. Okay. And so we have the u partial x plus v partial u partial y. And if we go back to the heat equation, we can see that we have basically the same thing right here. Okay. Right. And so in green, what we have are what I'd like to call the convection terms. Notice how each of these two, terms are paired, right? And so we have u times partial u partial x, okay, and then v times partial u partial y. And so there's a velocity multiplied by a derivative, and then a velocity multiplied by a derivative, okay? And so that's true on both sides, okay? For both the heat equation and Navier-Stokes. And so physically, what these terms represent is the fact that our quantity of interest can flow along with the fluid. Okay. Or in other words, another way we can say it is that our quantity of interest can be transported by a flowing fluid. Okay. And so if we look at the heat equation, we can see that our quantity of interest, which is temperature, right? And so if we have a fluid flow situation, then that temperature or that energy can flow along with the fluid, okay? Right. And so the direction of the flow can determine how that quantity gets transported. Okay. And so, at this point, you might be thinking, wait a minute, right? And so that makes sense for the heat equation because we have a temperature, which represents energy, and we have our velocity, right? And so that fluid flow velocity can push that temperature or push that energy down the river bend or something like that, right? But for Navier-Stokes, our quantity of interest is actually velocity itself, right? And so you're telling me that velocity itself, that velocity can carry itself down the path of fluid flow. And so not only is fluid flowing, it's also carrying its momentum along with the flow. And the answer to that is yes, that is exactly what's happening. And that's exactly why Navier-Stokes is really hard to solve, is because we have what's called here a nonlinear term. And so we have the quantity of interest itself, which is velocity, and that velocity is also affecting its solution. So it's a very kind of cyclical, nonlinear thing, and that's kind of what makes it hard. And so I'm not going to get into it anymore, but just know that. And if you had me for fluids, maybe you remember that the primary reason that Navier-Stokes is literally impossible to solve is this guy right here. Because we have velocity times velocity, and that makes it really difficult. Okay. All right. And so that's the convection term. And so that's the next important term. Okay. The next terms I'm going to highlight. So I'm going to skip pressure for now because pressure is kind of a unique thing. Is I'm going to circle these terms with the second derivatives. Okay. So let me go ahead and circle that in the heat equation. Okay. Right. And so these terms are what's known as the diffusion terms. And so what does diffusion physically represent? And so diffusion physically represents a passive spreading of a quantity of our quantity of interest. Okay. And so if you've ever sprayed a can of Lysol or a can of aerosol, you've probably seen diffusion take place, right? And so if you have a completely still room, and so there's no airflow or anything, and you spray a can of Lysol, or maybe more inappropriately, maybe you fart in the room, right? And so what you'll notice is that even without any airflow, that smell kind of spreads naturally throughout the rest of the room, right? And so that's diffusion. And so diffusion basically says that whenever you have a concentration of something, whether it be energy or whether it be momentum, that's just by itself is going to spread kind of passively and spread equally in all directions. And that's what diffusion is. Yeah. Or vape tube. Yes. Okay. And so I'd say those are the three primary terms, and those are the three terms that we're going to focus on a lot in this class. But there are two more that I want to cover, but of course we ran out of room here. Okay. All right. So before I move on to the next page, are there any questions on this? Okay. All right. And so the next term I want to highlight is maybe a connection you might not have seen. Is I'm going to connect the gravity term to the thermal production term, because both of these kind of do the same thing. Okay. All right, and so both of these terms, I would characterize them as something called a source term. Okay. And so what these terms represent is they represent the fact that our quantity of interest can be spontaneously generated or destroyed within our medium. Okay. Okay. And so I think the easiest way to visualize this is with gravity, right? And so if you, let's say that you have teleportation just for a second, right? And so let's say that you teleport yourself, 5 feet into the air, right? And so you're not going to be doing anything. So you just teleport yourself up and you're just going to just do nothing, right? And so just spontaneously, because of gravity, your body's going to start to have momentum, right? Because gravity is going to pull you down, right? And so gravity, you can almost think of it as a way to kind of spontaneously generate momentum to our object of interest, right? It's the same thing for thermal production, right? So thermal production is a little bit more difficult to visualize, but think of like an electric heater, okay? And so an electric heater, what that's doing is that it's taking kind of electrical energy and then converting that to thermal energy. And so it's almost like we're kind of creating thermal energy from nothing, okay? Right, and so both of those terms, thermal production and gravity, kind of represent the same thing. Okay. All right, and so that's the main connections between Navier-Stokes and the heat equation. But we have one more guy here, okay, and that's the pressure term. And so I'm not going to forget that. Pressure term is kind of like the odd man out, and it's also kind of a pain to solve, right? And so the pressure term, this is something that's unique to fluids, and so the heat equation doesn't have something like this. Okay. And the role of pressure is just to act as like another force that can drive a fluid forward. Okay. Okay. All right, so in this class, we're not really going to do anything with the pressure term, just because we're going to have our hands full just working on the heat equation just by itself. But if you do plan on taking like a CFD course later on, then this will actually be a big focus for you. Okay. Unfortunately, we don't have a CFD course here at Cal State Fullerton yet. And so I've been kind of talking with Dr. Myral, and we're thinking maybe we can develop a CFD course this summer. But he's really busy, I'm really busy, and so it's kind of been hard for us to find the time. And so we really want to make a CFD course because we feel like that this course doesn't it kind of gets you to that point where you can do CFD, but there's just not enough time in the semester to really get to it. And so yeah, so if you're graduating this semester, I'm sorry, I don't think we can finish it in time. But maybe sometime next year, we might have the CFD course where you can do it. But yeah, pressure term is something that's unique to CFD, and we're not really going to be doing anything for this course. But I did want to make you aware of it, and I wanted to point out that it's different from the from the heat equation. Okay. All right, and so those are our equations, right? And so two equations that you've probably seen in very, very different contexts, but hopefully what I've shown you is that they have a lot of very strong similarities, okay? And these descriptions that I have for you for about unsteadiness and convection and diffusion, I want you to keep these in mind because the physical intuition behind these terms is going to drive how we discretize them and how we actually implement them in code, okay? So their physical intuition is something that's really, really important. And we'll go through it, again, later on this semester. But I want you to kind of make that connection between the mathematics and the equation and what they physically represent, right? Because in engineering and applied sciences and in applied sciences in general, we have the benefit that most of the equations that we're working with, they represent some physical phenomena, and so every term, every variable that you have in your equations, they represent something physical, and so. It always helps, at least for me, it always helps to look at these equations and think about, what is that physically representing? What phenomenon is that physically representing? Because it's never just random variables, and so they always have a purpose. And so I want you guys to remember that purpose and think about that, especially once we start working with the code and working with, the computational algorithms. Okay. Okay. And so with that said, because we're seeing a lot of strong similarities between these two, we're going to work with kind of a slightly modified versions of these equations for this class. Okay, and the reason is, just to show you that these methodologies can be applied to other things as well. Okay, and so I'm going to take the heat equation. And I'm going to replace the symbols with other ones, just to kind of show you that this works for kind of any conservation equation, right? And so what I'm going to show you here is what I like to call the generalized conservation equation, or the general conservation equation. Okay. And one thing I actually didn't mention here is mass transport too. I know we don't have a mass transport class here, but mass transport actually follows a lot of the same rules as heat transfer. And in fact, its equation is identical as well. And so this equation I'm going to show here actually works for mass transport as well, right? Okay, so the general conservation equation looks like this, okay? And it has all the same players that we've seen before. Okay? The only thing is I'm just going to replace the symbols with other stuff, okay? All right, so first we have our unsteady term, and so we have partial phi, partial t, okay? And so that symbol that I'm drawing here is a phi, and so it's a circle with the line through it, okay? Okay, and so there we have our convection terms. Then we have our diffusion terms. Okay. Plus Q, okay, and that's our source term. Okay. And so here is our general conservation equation. Right. And so this is the equation we're actually going to be working with, throughout the semester. Okay. And just to kind of highlight to you where each of the terms represent, I'm going to use the same colors as I did before. Right. And so the unsteady term is going to be highlighted in red, which is, remember, our term with the time derivative. Our convection terms are going to be in green, right? And so remember, those are the terms with the velocities, right? Our diffusion term, which is in blue, is the term with the double derivatives, okay? And then, of course, we have our source term here, which is Q. Okay. All right, and so this is the equation we're going to be working with for basically the rest of class, okay? Or for the rest of the semester. Okay.
Is that coefficient gamma in front of the where you highlighted in blue?
Yes, yes, yeah. It's a gamma. Yeah. Mhm. Okay. And so you're not going to see temperature. You're not going to see, well, you will see velocity because it's in the convection part, but you're going to see a lot of feet, basically. Okay. Right. And that's it. And so that's all the review of heat transfer and fluids that you need. And so remember, I told you, it's the only thing you need to really remember is just the equation, and and we're going to be working directly off the equations, right? Some physical intuition is going to help, but we're definitely going to go through all of that as well throughout the class. Okay, but when you think about physical intuition, I want you to think about what does convection represent, what does diffusion represent, what does the source term represent, what does unsteadiness represent. Okay. And so, maybe this is a different perspective. At least I know it's different from the way I teach heat transfer, right? And so with heat transfer, when I teach heat transfer, I don't work as closely with the equations as this. And so, what I'm hoping for is that, this kind of gives you a different perspective on these equations and what they're used for. Okay. All right. Any questions on this? Okay. All right, and so for the rest of class today, I want to talk a little bit about, the process that we're going to go through in terms of, taking an equation like this and turning it into a computational code, right? So basically I'm going to talk about how the heck are we going to solve this equation, using computers, okay? And that process is what I like to call the discretization process. Okay. All right. Because if you look at the equation that we had on the previous page, and I asked you to solve that, probably most of you, unless you're a genius, you'd probably say, I have no idea how to solve this, right? And so, we're not going to solve these equations by hand. We're going to ask the computer to do it. Okay. But remember, remember what I talked about before. When you ask a computer to do something, you have to be extremely precise because you have to treat the computer like a baby. Okay. And so there's kind of a very defined set of steps that you can take to take an equation like that and actually solve it in a computer. And so those are the steps that we're going to do here. Okay. Right. And so in other words, one thing we need to do is we need to take our equation, take our problem, and break it down into steps that the computer can actually solve. Okay. Okay. All right. And so the first step in this process is what I could call define the problem domain and relevant physics. Okay. And so in other words, you're just defining the problem, okay? And so this step is true no matter what you're going to do in engineering, okay? And so whether you're going to use computers or you're going to use analytical or you're going to use experimental methods, you have to define the problem, okay? All right. And so some questions that you can ask yourself is to say, what's the domain, and what kind of physics am I trying to solve, okay? Okay. Another word for physics is equations, right? And so you want to determine what equations you're trying to solve, okay? Okay. All right. And so visually, it might look something like this. And so, maybe you have your domain is this kind of arbitrary potato. Okay. And then your equations, are defined by, whatever kinds of problems that you're solving. So maybe you're solving a heat equation, okay, or maybe you're solving a Navier-Stokes, right? So you need to determine, what are my governing equations here? Okay. And so, let's say that is the heat equation. So you have partial T plus U partial T partial X plus yada, yada, yada. Okay. Okay. And another thing that you have to define at this point is you have to define what are known as boundary conditions. Okay. Okay. And so boundary conditions, we'll talk a lot more about these later. Boundary conditions basically define how your solution behaves at the boundaries of your domain, right? And so your domain is always going to have some kind of boundary or some kind of outer part of it, right? And so your boundary conditions define, how the solution behaves on those areas. Okay. All right. Any questions on this? Okay. All right. So after you define your problem, the next step is to discretize your domain. Okay. And so if you've taken finite elements before, this is basically the process called meshing. Okay. And so the idea with domain discretization is that most geometries of engineering interest are too complex for a computer to analyze on its own. Okay. Okay. And so the idea with meshing, or the idea with domain discretization, is we want to take that geometry and break it up into a bunch of simpler shapes. Okay. Okay. And so let's say that we have your arbitrary potato like this. Okay. When we discretize it, it's literally going to look like we put like a wire mesh on top. Okay. And so instead of having one big amorphous blob, what we say is that, you know, we're going to have a bunch of squares that kind of make up this amorphous blob. Okay. And how coarse or how fine we choose to have our mesh, you know, that's an important decision that we're going to have with regards to our computational cost and accuracy. Okay. All right. You can almost think of it as like, you know, we're taking our geometry and we're pixelating it. Okay. Okay. All right, and so the next step in the process, once we have our domain discretized, is we have to take our governing equation and then discretize that. Okay. And so that's the step known as equation discretization. Okay. And so the idea behind the step is that, you know, usually our governing equation is some kind of very complicated differential equation. Okay. It turns out that computers are actually really bad at solving differential equations. And actually, you know, I can even just say that they physically can't. Okay. Okay. Or I guess I should say that computers can't solve differential equations on their own. Okay. But what computers are actually really good at is they're really good at solving algebra problems. Okay. And so our goal, or you know, our you know, what our objective is, you know, in this stage of the process, is to take a differential equation and then convert it into an algebra problem. Okay. Okay. And this is where we're going to spend the majority of the class, or the bulk of the class time, is, you know, how do we take a differential equation and then convert it into a basically a system of algebraic equations. Okay. And so let me go ahead and highlight this in orange. Okay. Because that's basically what we're going to learn to do in this class, right? And so a lot of computational techniques, and so you know, probably you've heard of the finite element method. In this class, we're going to learn different techniques known as finite difference and finite volume. You know, they all kind of do it in a different way, but their objective is the same. And so whenever you have a method that's like finite something, finite difference, finite volume, finite element, their goal is exactly the same. And so they take a differential equation and then they convert it into a system of algebraic equations. Okay. Because if you can do that, if you can convert a differential equation to an algebra equation, then your computer would be like, I got you, bro. I can solve it from here. Okay. But it's getting to that point. I think that's where it's difficult. Okay. And then writing the code to do that is also going to be the challenge. Right. And so this step 3 right here, equation discretization, I think this is going to be, I mean, that's kind of what this class is all about. And that's kind of the novelty of this class. Okay, any questions on this? Okay, all right. And so the fourth step, which is actually the easiest step, you know, once you've discretized the equations and you've kind of written the code to do that, the last step in the process is to just solve it. Okay. And so you probably think of, how can this be the easiest step? You're solving the equations. And so usually when you solve stuff, that's the most difficult part. But the nice thing is here is that, once you've kind of set up everything, the solving is done by the computer. Okay. Okay. And so if you remember from your linear algebra class, one way that we can represent a system of linear equations is to have it in matrix form, right? And so you might have seen a system like AX equal to B, right? Where A is some kind of coefficient matrix. Okay. X is the vector of solution variables, and B is the right-hand side vector. Okay. Right. And so that's kind of the matrix form of a linear set of equations. Right. Although probably from your linear algebra class, you're probably used to, maybe in the worst of cases, this being like a 5x5 system, right? Like your solution, your coefficient matrix A would be like 5x5, and your X vector will be like 5x1, and your B vector will be 5x1, right? And so you have a system of 5 equations and 5 unknowns, and that's represented by this system, right? And so you probably, and I was the same way, right? And so in your linear algebra class, you might be, saying, oh, 5 equations, 5 unknowns, that's going to take forever to solve. It's going to be so tedious. For this class, it's not going to be, it's going to be actually very common. Instead of 5x5, we're going to have systems of literally tens of thousands of equations and tens of thousands of unknowns, right? And so this might be like 50,000 by 50,000. Okay. This is 50,000 by 1, 50,000 by 1. Okay. And I'm not kidding, and that's actually a very light system too. And so, there's more that, for some really heavy codes, it can get into like the millions or 100 millions of size, right? And so you can see that practically this is, I'm not going to say it's impossible because, I've seen people do like 10,000 piece puzzles, and I'm like, why? But, but it's also it's going to be very difficult to solve a 10,000 by 10,000 system of linear equations. But, the good thing is that computers are really good at it, and they like it too. And so, that's one thing that we're leveraging in this case, right? The difficulty of this class is just kind of getting to this point. But once you get to this point, then the computer can kind of take it from there. Right? All right. Any questions about this process? Okay. All right. And so, there's one more thing I want to go over today, and that's the idea of approximation, error, and convergence. Okay. And I think that's kind of a nice way to end our first kind of real session here. Okay. All right. So one thing I want you guys to keep in mind, and I want you to kind of remember this throughout this entire class, is that when you do computations, like when you take a computational approach, it's what I like to call an approximate technique. Okay. And what I mean by that is that it's never going to be exact. Okay. And there's kind of two levels to this as well, right? And so when you do a computational technique, you're never going to solve your governing equations exactly. Okay. Okay. And so if you just kind of take it just purely as a math problem, right? And so we're basically solving the math problem of what's the solution to this differential equation. We're not solving that math problem exactly, right? But there's kind of another layer to this too. Whereas, even that equation itself, is not an exact representation of reality too, as well. Okay. Okay. And so everything is approximate, right? And so, when you get a computational solution, just remember that this is an approximate solution. It's not an exact one. We want it to be as close to reality as possible, and a lot of times it is going to be very close. But just remember that it's never going to be perfectly exact. Okay. And so kind of always kind of remember that whenever you do any kind of computations or any kind of simulations, it's an approximation. It's a prediction. It's not it's not exactly this is going to be the same. Okay. And so to that end, we have this concept of error when we do computational work. Okay. And so when we say error, we mean basically the difference between our approximate solution or our computed solution versus the exact value. Okay. Okay. And so we can define error kind of very simply as error is equal to approximate solution minus exact value. Okay. And so that exact value, it can either be like the exact mathematical answer to the equation, or it can be, what it physically kind of represents. Okay. Right. And so there's always going to be some degree of error, right? And so I think, I see that this is true kind of whenever I talk to people kind of outside the computational community, that when people talk about error, they think about oh, we have to eliminate error, right? Or we have to get rid of error because any error is bad, right? Whenever you do computational work, you can't get away from error. So error is always going to be there. And so the question is, we don't want to eliminate error, because it's always going to be there, but we want to minimize it as much as possible. And so we want to make sure that we're doing our techniques, we're doing our discretization, we're doing our computations as good as we can to kind of make this error as small as possible. But it's literally impossible to get rid of error, whenever you do any kind of computational work. Okay. A lot of times, that error is going to be, very negligibly small. It might be 0.000000000000000001, right? But it's always going to be there. You literally just can't escape it, right? But you just try to kind of minimize it as much as you can. Okay. All right. And so with that said, that kind of begs the question of, what can we do to kind of minimize that error? Question. So what would the difference between negative and positive error? No, it's a good question. So right here, this is kind of just a conceptual equation. And so, in reality, you would kind of always want error to be positive. And so you can just add kind of absolute values here or something. Or another way that people do it is they kind of take what's called the mean square error. And so they kind of square this, and then they take the square root. And so that kind of ensures that it's always positive. But yeah, there's actually, a lot more advanced error metrics out there. So there's actually more sophisticated errors, measures of error. This is kind of the most naive way to kind of define it, but it's more just a conceptual thing for now. Yeah. Mm-hmm. All right. And so, there are lots of things that we can do with the discretization in order to minimize the error, okay? Okay. And remember, from the previous page, we saw that there's kind of two levels of discretization that we have to do, right? And so on the one hand, we have domain discretization, right? And remember that refers to the mesh or the breaking up of our physical domain, okay? And then we have equation discretization as well, right? And so there are things that we can do on both levels here to minimize our error as much as possible, okay? All right, and so for the domain discretization, one thing that we can do to minimize the error is to minimize the spacing of our grid, okay? Okay. And so remember, the idea with this domain discretization is we take our physical domain and break them up into a bunch of, tiny, simpler shapes, right? And so the idea is that, the smaller shapes that we use, right? And so we in other words, we make the grid spacing smaller, then that's going to increase the accuracy and reduce the error, okay? All right. And so for the equation, and another way that we say when we minimize the grid spacing, another way that we say that is we're refining our mesh, or we're reducing the size of our elements, or the size of our grid. Okay. And so for the equation, the way that we minimize the error through our equation discretization is through the use of higher order methods. Okay. For most of you, that should mean absolutely nothing right now, and that's on purpose, right? And so that's something that we're going to explore, through the class as well. But basically, in the way that you take that equation, the differential equation, and the way that you break it up into an algebraic equation, there's what you'll see is there's lots of different ways that you could do that, and there are some methods that are better at this than others. But it also comes at a cost too, right? And so generally the harder, or the more that you want to reduce the error, the more expensive the simulation is going to be, okay? Because when you run these simulations, it's going to take your computer some time. It's going to take it some memory in order to perform the simulation, right? And what you'll see is that the more you want to minimize the error, the more expensive the simulation is going to be. And so there's kind of this trade-off of, how much accuracy do you want? How much do you want to minimize the error versus how much cost can you tolerate, right? How much time do you have to run the simulation? How much memory do you have on your computer, okay? And so there's kind of always that trade-off, okay? And there's not always a clear answer, right? And so, deciding when, you need more accuracy versus when you need a more efficient simulation, there's not a clear-cut answer to that. And that's something that you can always adjust, as a computational engineer. Okay. All right. Any final questions on this before we wrap it up for the week? Okay. All right. And so that's all I had planned for today. And so I believe next week when we meet again, what do we have? So next week when we meet again, we're going to do a review of mathematical concepts and MATLAB. Okay. So just to kind of prepare us for for the weeks ahead. Right, and then we're going to start by learning the finite difference method. Okay. All right. So thank you, everyone, for tuning in today. Hope you guys enjoy the rest of your evening and the rest of your weekend, and I will see you on Monday.
Thanks, Dr. Chan. Have a good
Thanks,
weekend.
guys. Thanks. You too.
Thank you, Professor.
See you next time.
See you next time. Hey.
I'll say hi. Can you say hi?
Hi.
Can you wave hi?
What's her name again?
Melody,
Melody. Oh, hi Melody.
say bye-bye.
Bye.
All right, I'll try and see you later.
All right, see you, Eddie. Have a good weekend.
You too.